Hi. If you want to follow along with this tutorial, you have to clone or switch to the branch O2 Vulkan renderer init. I'll be starting on this one. Before we get to the renderer, we have to fix the platform create window. While programming for this tutorial, I noticed that the hwind that we get here is not correct. We have to supply this by pointer and then change every window to the pointer of the window. And we can also specify 0 here. It doesn't matter. Put this to 0 and the pointer here. This will make it so that this function sets the window for us. And then down here in main, we can actually use the pointer to the window because we'll now be supplying this window to the Vulkan init function as a value though. Inside the Vulkan init, we add the void pointer window. I use the void pointer here so in the future when we for example do a Linux build, we can use a different window here and it should still work. The next thing I want to do is define a Vulcan macro. Find vk check. It takes in a vk result and what it does is it if checks against the result to be unequal to vk success. If so, we are going to do a debug break, which is a compiler specific call. I'll show you what that means in a second. It's basically what it says, a debug break. So, but before we do that, we do std cout result std end line. Then we have to end these backslashes here to the end of every line, and that's it. Now, instead of doing this if check here, we can do vk check vk create instance. And all of this goes away. And then obviously it's complaining because we didn't include IO stream. Kann ich bitte schreiben include IO stream. I want to change it now to return true when it reaches the end. So I'll expand this macro to include the return of false. Now, whenever this isn't true, it will return false and the vk init function will not succeed. Let's compile and run our program real quick. Still works fine. Make sure that this actually works. We're gonna put a equal here, compile again and see, boom. It hit the breakpoint right here. And in the debug console, it detected a Vulkan error code, which is 0. We can also expand this and say, well, give me the Vulkan error as a result. Boom. Compile and run again. Check the debug console. Vulkan error 0. Or in this case, you can then go to the browser and do vk result. What is the Vulkan error that we get? Oh, we got vk success. Nice. This is kind of helpful to debug Vulkan, but set that back for now and compile and run again. We will expand this later. Okay, so the next thing we need to create, we open the Windows window and what we now need to do is create a what is called surface, Vulkan surface. So we type in vk create surface and we notice there is no surface. Well, I happen to know that we actually need an include over here. And this include is include Vulkan win32.h. And then if we go down here, we can do vk create surface. And then we get this vk create win32 surface khr. What do we need? Well, we need a vk instance. We have that. We need a surface create info khr. Okay, surface info pointer. We need the allocator. We set that to 0 and the surface, which would be vk context surface. And the pointer to that. Boom. Let's create the vk surface khr. Khr means Chronos. This is actually an extension and you'll see what that means in a second. Tap in the surface here and then we do vk win32 surface create info. Boom. Surface info. Initialize that to 0. Very important. It is a struct again. Like with every Vulkan object that you create, you have to fill in a structure. So the surface info dot. So the S type is the same. It is vk structure type win32 surface create info. Surface info. What else do we need? Well, for this, we need a hwind. This is the one that we supplied. We turn that into an hwind handle window. Checking out what else we need. We need an h instance. Luckily, we don't have to supply that. We can just do get module handle a 0. This will give us the h instance that we need. And this is it for the surface. And then we create that. But we have to remember, we do vk check to see if it actually works. Let's compile and run again. Press F5. And it doesn't work. Well, why doesn't it work? We get a Vulkan error -7. Okay, what is -7? vk error extension not present. Remember earlier I told you that we need an extension? Well, we have to load this. And in order to do so, we supply an array of extensions to the instance when creating the instance. So over here, if you check the instance info dot, we see enabled extension count pointer enabled extension names. And I like to define them like this. Just on the stack. Char pointer to extensions array. And luckily we have a macro for the extension name. These are char pointers. But what we can do is the extension is called vk khr for Chronos surface extension name. And then boom, close that with a colon. The info.pointer extension names is then extensions, and the extension count, we could leave the extension count at 1, but I like to define a macro for that too, which is called array size. It basically takes in an array and does size of array divided by size of array on 0. And so the instance info.extension count is array size extensions. Boom. Now we supply that extension. Let's build and try to run again. Oh, we get another error. What is the problem? Oh, same error. We don't have the extension present. That is because we loaded the extension, the surface extension, but we also need to tell Vulkan that we are using a Windows surface. And that Windows surface is a vk khr win32 surface extension name. When we load this extension now and compile, it works. There's no error coming again. Now, I don't want to have this Windows specific, so I'll set myself up for later by doing if def Windows build and if and elif. This would be a different OS, other OS, and I'll add these everywhere. If def Windows build, hashtag elif, hashtag endif, boom. And for the surface as well. If def Windows build and if. Try to build. If we now compile and try to run our program again, we first get this invalid integer expression. I've done some research and it looks like we have to define a constant for this to work. So we have to do d/d Windows build. Then this will compile. The error before was basically telling us that elif didn't have any checks and therefore it didn't know what to do. To make this safer, we could add a, I don't know, Linux build over here and then replace every line. We basically don't do anything on the Linux build. Let's try to run again. Everything's still working. Good. To be honest, this Linux build being white is pissing me off, but I'll continue. Anyways, I like to create what is called local scopes for every single Vulkan object that I create. So this would be create surface. And the next one we do is choose GPU. That's fun. In order to choose a GPU, we need to query the GPUs, and we can do that by vk enumerate physical devices. For that, we need a vk context instance, device count, GPU count, pointer, and a pointer to physical devices. We'll leave that to 0 for now. The way this works is that we first have to query the count, and then we do the same call again, and we get the properties of the GPUs back. So we define a uint32t GPU count is 0. Boom. And then we call the same call again, but this time we need to define an array. And what I'll do for now, I'll add it to do here. Later on, we're gonna do sub allocation from main allocation. For now, we're just going to do a vk physical device array GPUs. We serve 10 spots and we pass in the GPUs. A quick check if this has a vk result. Yes, it does. Then we do vk check because this could actually fail. Once we have the GPUs we want, we loop over the GPUs by doing for uint32t I is less I0, I is less than GPU count I++. Okay, so what do we need to do? First, I like to do vk physical device GPU is GPUs on an I, just so it's easier for me to talk about the GPU. The first thing we need to check for every GPU is if it can actually do graphics. And what that means in Vulkan is we need to check for what is called queue families. Queue families describe what type of commands can be executed. We want a specific queue family that lets us do rendering commands. And we can query the queue families of the GPU to test if they can do graphics. And this is what we are doing right now. First, we actually need to evaluate what type of queue families we have. And this is by, of course, a simple call called vk get physical device queue family properties. We need a GPU, we need a queue family count, pointer to queue family count, and the properties is 0. It's the same thing. We have to call this twice, like above. We do uint32t queue family count 0. And the same to do as well. Yoink. We will sub-allocate from main allocation later. I should learn to spell. It is Q. What we'll get back is a VKQ family properties. You notice that there is a 2, for example, over here. I don't 100% know what the difference between 2 and the actual one is, but there is a difference. But calling this one is fine. I know that it has something to do with the version and what we get back, but for our purposes, this is fine enough. If you want to do further research, I recommend looking on the Discord server for Vulkan, or maybe reading up in the Vulkan specification, although that didn't tell me much when I was researching this. So yeah, anyways, we're gonna call this Q props. And same thing again, we're gonna do 10. I know this isn't optimal, don't hate me. I just like to do it this way because I later on want to do a main memory allocation once and then sub-allocate from that memory so I don't have any dynamic allocations during runtime. I have been infected with what is called a handmade hero disease, and he likes to do it that way. And since I've seen that, and after trying this out, I couldn't revert back. I really like the idea of allocating once and then never allocating again. Sue me. Anyways, you could also, for example, use an std vector and vkq family properties over here. That's up to you. I like it that way, and that's what I'll do. Once we have the Q families, and again for those ones, check, oh, this doesn't return a VK result. Okay, we don't need to do VK check. We now need to loop UN 32T, J is 0, J is less than Q family count, J++, boom. And for now, the only thing that we need to check is if Q props on J dot Q flags and VK Q graphics bit. We're basically testing if the graphics bit is set in this queue. If so, we need to store this index J, because this is the index of the Q family that we will be using later to do graphics operations. So we store that in the VK context as a graphics edx index J. And we break. We found one, it's fine. Now it could be that none of our GPUs actually support graphics indices, so we have to check here if the VK context graphics edx is less than 0, we have to return false, meaning we can't continue. And I freaking need to learn to spell. Let's add that in the VK context, call this int graphics edx. But that's not all. We also have to set the VK context graphics index to -1 when we choose a GPU. It would be nice if that was it. But sadly, we have to do one more thing, and that is we have to check if the GPU supports presenting images to the surface we created above, meaning to the window. So basically, once we have found a queue that is capable of doing graphics, we also have to check if that GPU using that queue can present images to our surface. And we do that by calling vk get physical device surface support. KHR. We type in the GPU, we take the Q family index, which is J. The surface is VK context surface, and the support would be surface support. That's a bool. We have to define that VK bool 32 surface support. VK false. And I should freaking learn to surface support spell. We query that and then we check if we have surface support. We can do all of that. And if not, we can't. Obviously, since we want to choose a GPU, we also have to set that context. GPU is GPU. And obviously we don't have that, so put in the GPU over here. VK physical device GPU. I like to call it GPU because the next thing we create is a logical device. And it can be very confusing having a physical and a logical device. This is the GPU in my mind, and the logical device is just the device. But first, let's try to run this. Didn't work. Great. Why not? Oh, first of all, I forgot to do a VK check here. Oh, I found the problem. I'm stupid. I need to add the Q props in here. Yep. Don't ever copy and paste. It's stupid. Okay, this should work. Yep, it works. Okay, so we found a suitable GPU. Okay, the next thing we create is a logical device. And I hope by now you notice how I like to do things in Vulkan. I don't actually know what I really need to do here, but I know the call, which is vk create device. And then I can look, okay, so I need a physical device. Well, that would be the vk context GPU. I need a what is called vk device create info. Okay, device info. Callback, nope. and then the pointer to the device, which would be vk context device. And I like to do this from the bottom to the top, right? I want to create a device, I do the call, I check it with IntelliSense what I need to do, and then I just try to supply everything that I need and check if that works. So the first thing we need is a vk device create info. Device info, boom. Let me put this up here a bit. So the device info. Obviously we need to have an S type, vk structure type device create info, boom, device info dot. And now we have the same thing that we have with the instance. We might need extensions, but I'll omit them for now and see if this causes an error down the road. I like to test things like this so I know what not to do, because I feel like this is a better way to learn stuff than doing it right the first time when you're trying out something and then wondering later on when you're not doing it exactly the way you did it before, why it fails. I like the idea of playing around and then seeing what happens. So we're not gonna do any extensions. So yeah, we don't do anything here. Let's add the device, vk device to the context. And we probably have to do a vk check here. Stuff like this always wants to return a bool. And let's see if that actually works. If that works, we created a logical device. This logical device is used in almost every single Vulkan call later on. We need that, it's very important. This will probably not be enough. But yeah, anyways, the next thing we need to create is a swap chain. And I think I need to explain what a swap chain really is, because when I first read what a swap chain was, I didn't understand shit. So I'll try my best to give you my understanding of a swap chain. And I think the best way to do this is by doing this. Let's say we want to draw a circle on even frames and a rectangle on odd frames. So I drew two images here, a rectangle and a circle. Well, what is a swap chain? My understanding of a swap chain is I go to the swap chain and I ask it, well, give me an image, please, so I can draw. And the swap chain is like, yeah, here you go. That you can use that. Then I draw my circle, since this is the first frame, and I present that circle to the screen. While this image is being presented, I want to draw the next image. So I go to the swap chain like, give me an image, and it gives me another image. This could be the circle image, but it doesn't have to be. It has more images. It can have more images. So it gives me this empty image, and I draw the rectangle on it, and then I present. And basically what is happening is this. It's like, these are the different images being displayed. And the swap chain just manages these images for you. It's like you can index into these images and draw on them and then present the image. This means this, but this also means you will have to do a lot of synchronization, which we'll see later. But yeah, anyways, that's my view of the swap chain. You basically ask the swap chain for images, and when you create the swap chain, you have to specify the dimension of these images. That's the most important thing, and what they look like. And this is what we are doing now, swap chain. So yeah, like with every other function call, we do vk create swap chain and see what that brings us. Okay, we need a device, vk context, we have that device, right? This is the device that we are using. We need a swap chain create info khr. Okay, so the swap, I'm gonna call this sc info, swap chain info. Allocator 0 and the actual swap chain. So vk context swap chain. When we do vk swap chain create info, sc info.s type probably, yep. vk structure type swap chain create info, and let's look what we need. sc info dot, we need a whole bunch of stuff. If we go through those, we can see image extent, image format, the color space, the image usage, how many images the swap chain will have, like the images that I told you before. There's also a present mode. This means how the images are presented, and this can be a little confusing, so we're going to take this very slow. Let's start with the image usage, because this is something we can use, we can define directly. And this will be vk image usage. And then we can look at all of these different image usages, but we want the image usage color attachment bit. We can also Google this over here. Specifies that the image can be used to create a vk image view suitable for use as a color or resolve attachment in a vk frame buffer. Doesn't tell me much. The next thing we can specify is the surface, which would be vk context surface. Let's also add the vk swap chain khr. And I guess we can just do a vk check here. See if that actually is enough. to create the swap chain. Because I'm curious what happens now. Interesting. I guess we get an access violation executing location. Let's try to fix that. After trying around a bit, I found out what the problem was. Remember the queue earlier that we got? It is trying to access a queue that we have not created when creating the device. Let me show you what that means. In the device info, there is a pointer queue. When you create the device, the queue will be created as well. So we need to specify what type of queue we want to create when creating the logical device. Let's just do this queue info, device info.queue count. It's 1. And we specify vk queue create info, queue info. So what do we need here? Queue info dot. Well, the S type is obvious. vk structure type queue create info. Boom. Queue info dot. And this is where we need the queue family index again, which is vk context graphics index. We want to do graphics queue info. Do we need anything else? Oh, we need the queue priorities. That is a pointer to a queue priority. This is the priority for the commands we will be recording later. And you can specify the priority by using a float value between 0 and 1. 1 means it is the highest priority, 0 means lowest. So we're going to do float queue priority is 1.0. There's one more thing. We need the queue info.queue count is 1. And the same thing in the device info count, queue count. Here's 1. But the fact is the error doesn't go away. After doing a bit of research, I found out that we have to specify the extension. And even if you enable Vulkan validation layers, they will not show up an error when you create the swap chain. It will still be the same access violation that we get. So yeah, remember the extension that we had to specify for the instance. We also have to specify that for the logical device. In addition to the queue info that we supply. So we do char extensions array, and then we do vk khr swap chain extension name. We add that to the device info, extension names, extensions, device info dot extension count is array size extensions. We build and run, and we finally get a proper Vulkan error, which is -3. Back in here, we can look at the result error. -3 is vk error initialization failed. This, in my opinion, is a good point to enable validation layers. I've been talking about that before. It is basically a way of Vulkan telling us when something is wrong. Enabling validation layers happens at instance creation time. So the first thing we need to specify is an extension, like the swap chain extension. It is a vk debug utils extension name. We need the extension, and we also need what is called validation layers. I don't exactly why you need to specify both, but that's just how it is. So yeah, we're gonna do char layers array is vk layer coronos validation. I know that there is a constant that you can use, but I don't remember where to find that constant, so I just type that out. Now for the extension, we don't have to do anything, but we also have to supply the layers. The instance info pointer enabled layers is layers, and instance info layer count is array size layers. That should enable the layers, but we also have to create what is called a debug Utils Messenger. This debug Utils Messenger is an extension, and creating that debug Utils Messenger is a function that we have to load from the DLL. It is not by default included in Vulkan or something like that. And we do that by calling a function called vk get instance proc address. In here we have to specify the vk context instance and the name of the function that we want to get. And this is quite difficult. To type. It is vk create debug utils messenger extension. The return type of this function is the actual function. So we do auto, and I like to call the function by its actual name, which would be vk create debug utils messenger ext. If we want to have IntelliSense for this function, we can also specify the return type. Since this is void return type, we can do pfn, pointer to a function, underscore vk create debug utils messenger extension. And don't forget the semicolon at the end here. Now we can actually check if we got vk create debug utils messenger extension. Do we have the function? Then we call the function. What do we need? Well, we need an instance. No surprise here. We need a debug utils messenger create info extension struct. Okay, I like to call this debug info. Allocator would be 0, and then the vk context debug messenger. This is the actual debug messenger that we will be creating. If this doesn't return the function, we need to return false. Okay, the debug info. vk debug utils messenger create info extension, the debug info. There's a lot of stuff we can specify. Let's look. Obviously, the s type is vk structure type debug utils messenger create info debug info dot. The interesting things are the message severity, for example. We can specify using bits what type of messages we want to look at. You can specify these bits by doing vk debug utils, and you see that already. Message severity error bit. We want errors, and we want to have vk debug utils message severity warning bit. We want warnings and errors for now. Debug info. The next debug info that we want to look at is the message type, which would be vk debug utils message type. What do we have? We have general performance validation. We want to have anything that is general, and we want to have vk debug utils message type validation. And the last most important thing is the pointer to a function user callback. And I like to call this vk debug callback, which we haven't defined yet. We create the vk debug utils messenger, debug messenger. And now it's time for the function. The function has a very specific signature. Let me type it out and then we'll inspect. So we start with static, followed by a vk API attribute, followed by a vk bool 32, this should be the return type, followed by a vk API call. Yep. And then finally the vk debug callback name. The parameters are the vk debug utils message severity flag bits, the message severity. The next thing is the vk debug utils message type flags extension, which would be the message flags. And then there is a const pointer to a vk debug utils messenger callback data extension pointer, which would be the pointer callback data. And the very last thing is a void pointer to pointer user data. But we are not going to use that yet. This is the callback, and inside the callback we just do a simple std cout validation error with the message, which would be pointer callback pointer message std and line return false. Build that and see if that works. It does. And now we can actually see validation errors, which is a shit ton of errors. But this will help us to figure out what we are doing wrong in the future. For example, we create the swap chain and obviously we don't supply everything we need. So the first validation error that we get tells us that the pointer create info pre-transform must not be 0 when specifying the vk swapchain create info struct. I will now go through all of those and specify them.